Okay. So when you are taking, this is again a bicyclic molecule. What you can observe, this is 3, 1. Say why it is 3, you can observe 1, 2, 3 carbon atoms. So this is 1 carbon atom, that is this. This is one carbon atom, and total number of carbon atom is 7. So it is a heptane. Similarly, what you can observe here, so 1, 2, 2 carbon atom. This is 1, 2, 2 carbon atom. 1, 2, 2 carbon atom. 2, 2 carbon. Totally 3 cyclic, tricyclic. 2, 2, 2 decade. So this is how you can name the IUPAC nomenclature for the bridged molecule. Now I will go for a conformational analysis in bridged molecules. So what you can observe here, so you can observe that a bicyclic molecule. So this bicyclic, you can observe that this is a 6-membered ring. So that is the chair form is the more stable one. And this is the what you call a 4-membered ring, envelope form. Okay. So this is a envelope form. This will be the more stable one. And similarly here you can observe 6-membered ring and a 5-membered ring. So 6-membered ring chair form and the 5-membered ring envelope form. So that conformation. Okay. Right. So when you are taking this bicyclo 2, 2 peptide, so this is a 5-membered envelope form. So both are envelope. You can observe this also 5-membered ring, this also 5-membered ring. Envelope form will be the more stable one. So when you are taking a 8-membered bicyclo 2, 2 octane, so this form will be the stable one, and this is the conformation. Similarly, when you are taking these two bicyclic, the envelope form and puckered form. So this will be the stable one. So with this, I will go to the next slide. So next slide I'm going. Okay. So when you are preparing a adducts, these compounds are called adducts, and more particularly this kind of synthesis is called Diels order reaction. What is happening here, there will be a reaction. What is that? You can observe that 4 pi electron, 4 electrons are involved. That means this is 2 pi electron, this is another 2 pi electron, and this is another 2 pi electron. So this kind of moieties are called diene, and this is called dienophile. Reaction of diene and with the dienophile, just by combining and heating, will get an adduct, and this is what you can observe, a ring structure is obtained. So this was invented by the scientist called Diels Harder. Deal is one scientist. Harder is the student of Deal. So for them, for this invention, they got a Nobel Prize. And these kind of moieties are called Diels order products, or more particularly, it's called 4+2 cyclo addition. What is happening here? There is a possibility of forming a two products. One is endo product, another one is hexo product. So what I am mentioning is endo product. Endo product means these two groups are inside or near to this double bond. So because of this double bond, and there will be interaction between the non-bonding electron. Okay, non-bonding electron means lone pair present on this oxygen and double bond. So because of this interaction, this endo product is favored. Okay, so that means here also stereochemistry is there. The endo is one stereochemistry, exo is another. Exo means this hydrogen will come over here, So this CO O group is coming above. That is called exo. So normally in the Diels order reaction, only the endo product is formed. That's what I have mentioned here. So this is about the stereochemistry of Diels order reaction. Endo is the major product. So why it is forming? Because of, it is stable because of the interaction of bonding interactions, this pi bond interaction, and also in addition to that a non-bonding interaction with the pi bond. So that because of that endo product is stable. So then I will go to the next one. So next slide. I'm moving to the next slide. Okay, so here I'm taking a per hydro anthracene. So here what you need to observe, this is I think you are aware that if there is a double bonds here, it's means one double bond here, one more and one more. Okay, here one more, here one more, and here one more, here one more. So that is called anthracene. So if there is no double bond, it's called perhydroanthracene. So in this, you can observe that this is one ring junction between the A and B. Similarly, ring junction between the B and C. So what is you need to observe? So suppose if there is a two dots, you can say that cis. And this is and here what you can observe, if there is a two dots, this is also a cis. And for this is called cissoid. Cissoid means because here also cis there, here also cis there, then this will be the cissoid only. So the stereochemistry of this group is called cissoid cis. Okay, so how you can represent, you can represent cis, c, cissoid, cis. Okay, suppose if there is a one dot here and there is no dot, means this is a trans ring, and here one dot is there but there is no dot here, means this is also a trans. So the ring junction between A and B is trans, the ring junction between B and C is trans. What you can observe here, you can observe that these are in opposite way. So you can observe that this is the what you call beta, and this one is alpha. So that is the reason it's called transoid. So you can write the stereochemistry of this moiety is transoid, trans is the stereochemistry of this one. Similarly, you can observe that this is the trans ring, this is also a trans ring, and you can observe that this is also a trans. So transoid, trans is the stereochemistry of this moiety. Similarly, you can observe that this is one dot, there is no dot here, so trans. Similarly, what you can observe that here dot, here there is no dot, means it's a trans. So you can observe that both the thing are alpha one only. So that is the reason this is cissoid. So you can write trans, cissoid, trans is the stereochemistry of this perhydroanthracene. Similarly, you can observe that two dots is there. So this is cis, one dot is there, it's a trans. So when you are looking into the stereochemistry of this one, so both the side are towards the observer, yes, towards the observer. So it is a cissoid. So cissoid, trans is the stereochemistry of this one. So similarly, this see here there is no dot. There is no dot means both the hydroxy group is away from the observer. So that is the reason cis, trans, cissoid is the stereochemistry of this moiety. So with this, I will go to the next slide. So next I'm taking the stereochemistry of perhydrophenanthrene. So perhydro means there is no double bond. Phenanthrene means there is a double bond. So perhydro means there is no double bond. Here what you can observe, two dots. Two dots means it's a cis. And here there is no dot, means that is also a cis. But when it comes to a between these rings, it's a transoid one, because this is alpha, this one is beta. That is the reason this is a transoid. Cis transide, cis is the stereochemistry of this phenon 3. Similarly, you can look into that. So what you can observe here, uh, this is a dot and there is no dot, trans. This is a dot, there is no dot here, means trans. But what you can observe here, this is also a alpha hydrogen, this also a alpha hydrogen. That is the reason this is cissoid. So trans, cissoid, trans is the stereochemistry of this one. Similarly, you can write stereochemistry here. There is a dot, so there is no dot here, trans one, and this will be the cis one, trans, uh, cissoid. Trans is the stereochemistry of this one. So similarly, what you can observe here, there is a dot, but here there is no dot. This is the trans ring junction. So both the dots are there. So it's a cis junction. So here you can observe this is beta hydrogen, this is alpha hydrogen. That is the reason it's a transide. So transide, cis is the stereochemistry of this moiety. And